All right, so welcome everyone. Uh, I think it's Monday, so we have a list number of people, and the session is recorded. So we'll be sharing the recording to other participants. So today we have a speaker, Ash, who's an experienced developer in ZK World, currently working at Fuel Network. So happy to have you, Ash, and he'll be talking about ZK program, what to take care of, how to test with Circom and stuff. So yeah, Ash, you can go ahead and hope you can share your screen. You'll have the options as well.
Uh, yeah, I'm audible.
Yeah, you're audible.
Hello, everyone. So, yeah, my name is Harsh, and thanks for the introduction. And let me share my screen. Is my screen visible now?
No, it's loading. Just yeah, we could see it.
Okay, cool. So, welcome everyone. So, this is an old workshop that I used to give a lot in places when ZK snarks were very new and no one knew what they are all about. And before I start this workshop, so who is the expected audience for this? This is for someone who has never written a Circom circuit, who doesn't understand, let's say, what ZK snarks are, and who even needs to be convinced that they are indeed possible. So I would say that's the ideal audience. So if you're someone who has written circuits in the past, or let's say who has some experience with it, I would say this is not the workshop for you. But if it is, if you are someone who has never written a circuit in the past and wants to go through a ride that, oh, like ZK snarks are indeed possible and what's the basic construct of them, then this workshop is for you. At the end of this, I'm more than happy to entertain questions on any particular level. But yeah, like for the first 30 to 40 minutes is for beginners. And at the end, if someone wants to stick around and ask other questions, which could even be out of the scope of this workshop, I'm fine to answer them. Then yeah, more than happy. So yeah, let's get started. And this might have a little bit of the slides might have a little bit of outdated details about me, like where I work and things like that, because I sadly no more have the edit access to them, but gladly the link is still live. So I can still use it, but cannot edit the workshop. But yeah, so let's get started. In the meanwhile, I would advise for you all to uh, clone this repository locally if you want to follow along, although this will be recorded as well. But this is if you look here on this side of the screen, I have created a starter kit, which makes it very easy to write a first circuit. Otherwise, it takes a decently long time to get up and running. So hello, everyone. My name is Harsh, and I guess, yeah, the goal is to give a very succinct introduction to ZK snarks, convince you that they are indeed possible. So I will take the first 10 minutes to actually convince you that this stuff is possible and what an ideal flow of building your first Circom project would look like. So I guess now the word ZK is everywhere, but back then, like 2 years ago, it was kind of like a really hot thing. So I remember I won a workshop where I made a ZK ID based system, like a ZK voting system, and they gave me the prize for building a ZK roller. So like that's how complex ZK is, right? Like most of the people still really cannot differentiate like the term roll up and ZK, like the thing ZK is roll ups, right? So I guess like there has been a lot of confusion around the term, and I guess a lot of people even continuously tell me that they don't believe in the moon math and it's possible. So I guess we will just go through a very fast way of convincing you that it can work, or what the model is indeed. Of course, we cannot go into the detail of the protocol, but then we can talk about snarks, we can talk about Circom and snark gears, and then also attempt to build our first ZK applications. And at the end, I would also try to provide on my end an ideal roadmap of how I think you could really do something better beyond what we discussed in this workshop and possibly build some real things out of it. So what is ZK cryptography? Like it's a way to prove knowledge of information without actually revealing it. And it's a very interesting statement because like the natural question is like, how is it even possible, right? So so first, let's take a look at what does an interaction look like in any ZK based application. So you have two entities. There's a prover, there's a verifier, and the prover possesses some knowledge. It could be, let's say, a square root of some number. It could be the next state update for a roller, but it could be just any piece of information which can be computationally proven. And this prover is interested in proving to this verifier that he knows or she knows some piece of information which meets certain criteria that the verifier has. And these scenarios indeed are very true. Like, let's say, for example, if you go to some places which require you to be above 18 or 21, you usually end up showing them your passport or your national ID card, and all they really needed to know was, like, are you above 18? That's all they needed to care about. And that's kind of like the scenarios where zero knowledge proofs are really interesting, where you can prove certain facts, but don't, like, no need to reveal anything more around them. So yeah, like, that's an interaction. There's a prover, there's a verifier, and then the prover and the verifier communicate through this mathematical or cryptographic object called as a zk proof. So the prover, through some moon maths, can create a proof of knowledge, and the verifier can verify it. And then I just said a lot of stuff, but the question is that, like, how is that even possible? And let's say, how do we get some sense of understanding of how is it happening without actually going deep into the maths? Because I think zk cryptography is really interesting and easy to crack. But I guess, like, where people do go wrong is by giving a big mathematical introduction to them, rather than where all you have firstly have to do is just convince people that it's possible. So let's take a small detour and let's talk about computation, which we all are pretty used to, right? Like, what's a computation? You take a bunch of inputs, you do some processing on top of it, and voila, you have some output. And that's a computation. And then, so for example, multiplication of two numbers, x and y are inputs. There's a processing happening, which you could say is multiplication. And then there's some output, right? So that's a traditional computation. And how do you generally verify computation? Is that you usually recompute. So the prover says, hey, here are the inputs, here's the computation I did, here's the output. The verifier has some sort of similar computation machine, and he says, okay, like, give me the inputs, give me the outputs, and let me just verify the outputs myself by redoing the computation. And the core problem is that, what about really heavy computation? So imagine, let's say, imagine doing something which takes 2 hours or 3 hours to do, and then being able to convince someone that you indeed did it correctly. And that's where, like, trust starts leaking into such systems, right? Because now anyone rational who has outsourced computation, which takes a huge amount of time, won't actually re-verify it, because the cost of, if they could indeed recompute and re-verify, they would have never delegated, right? So in practical situations, this concept that you can always recompute to verify doesn't really hold, and trust always leaks into the system. And that's the, like, you could experiment with this new system, and this has been in computation from quite some time, and the concept is called verifiable computation, where, like, you change the computational model and you say, there are inputs, there is some heavy computation that happens, there's an output, but we do some extra steps to create this small object which we call as a proof of computation. And then the idea is that you can take this input, this proof of computation, and output, and then the verification can happen sometimes in constant time or sometimes in, like, very small amount of time depending on protocol. But yeah, so that's verifiable computation, that like, you can just prove computation by doing some moon math. And of course, we cannot go into the moon math right now, but I'm more than happy to talk a little bit about it later, or suggest some resources that could help you understand that how do we even get this proof of computation object. But the goal is to at least get to an understanding of the model itself, like this verifiable computational model. And yeah, I just talked a lot of stuff, but then the question is that, how is this really interested to, like, proving knowledge, right? Or let's say zero knowledge proofs. And then the question is, like, what if you could really hide some inputs in this verifiable computational model? Because if you go back to this model, like, you're still giving all the inputs, So that's an issue because we might want to hide some of the inputs. For example, if I want to prove that I'm above the age of 18, I would always want to hide the fact that where I live, which country I'm from. I would just like to prove that I'm above the age of 18. So, uh, yep. So what if we could just hide some, let's say, inputs, which means that uh, modify this again with some moon maths, and yeah, like have the ability to just give a proof of computation and some output, and that could indeed allow for verification of computation. And that's where you get zk based verifiable systems, where the prover could have inputs in a computation which they could hide when they send this computation for verification. So it means that in a multiplication example, you could hide x and y, and you could just give the output of x and y and give a proof of computation. And any verifier guaranteed by maths, or we could say moon maths, could verify this and be sure that you indeed know two number x and y, which when multiplied could result into z. So that's that's like a new model of computation, and that's kind of what snarks, or let's say zk based systems are like based upon. So you could say that if you have like verifiable computation and if you can hide inputs, it means that you can prove knowledge of inputs. And like the scheme where which we discussed, which is verifiable computation with the ability to hide some inputs here and there. Uh, so there are like multiple mathematical schemes through which you can get this. And let's say one of the earliest ones was snarks and starks. And when I created this workshop, snarks were like really popular. They still are, although a lot of cool work has happened in the starks, but we would be working with snarks right now. And what zk snarks are like, they allow you to prove in a succinct manner that you did some computation right, at the same time also having the ability to hide some inputs. And the way you express computation here is through arithmetic circuits. So like there are basic operations, addition and multiplication, and then you combine them to create complex computation. So that's the basic construct that you have, like you use these arithmetic circuits to express your computation, and then use certain techniques in between to give the ability for approval to hide certain inputs of this particular computation. And yeah, so they are like one of these schemes which makes it possible. And yeah, like if you run a zk circuit or a snark circuit, then you along with an output can also produce a proof of computation, which we call like as a zk proof. So, and often a question that is asked is that, like, okay, like can you only do primitive stuff, because these algebraic circuits look like you can just do addition and multiplication and very primitive stuff, but you can actually build like anything on top of them that is computable. Like you can build hashing algorithms and prove that you know some pre-image, which when hashed results into this some particular hash. So you can just go crazy and design whatever you want. Like when I was at Polygon ID, we created a whole identity system out of this. So yeah, like you can build whatever you want. And then one last thing before we actually get our hands dirty and start coding a little bit is the differentiation between public inputs and private inputs. So in this particular model, you can actually decide to selectively hide certain inputs and reveal certain inputs. And you can think of it as a contract between you and the verifier, where the verifier says that, okay, like I will verify your computation. And at the same time, I'm fine with you hiding some of the inputs, but I want some of the inputs to be public. And the question could be like, why would we even need public inputs? Right? What could be a real world scenario? But let's take a look at proof of membership, right? So if there's this particular prover who wants to prove that they hold an address in an NFT whitelist, then there would be two inputs, right? One would be an array of addresses, and ideally you won't do it with an array, you would do it with Merkle trees, but you would like feed in an array of addresses, and then you will try to your computation will just prove that you own one of the addresses inside it. So there would be two inputs, an array of addresses and your address. And then the verifier isn't interested in your address, but they are interested in that you own an address inside this list of addresses. So they will say that I need the first input, which is the whitelist, to be public so that I can verify that you indeed are part of the correct list, but I'm fine with you hiding uh, your own address. So that's one of the examples where you might need to leverage public inputs. So yep. So let's talk a little bit about building stuff. So what are we going to build? We are going to build this application called ZK Factors. And you could say this is kind of like an hello world of Circom. So if I guess everyone who's used to programming knows that the first thing that any programming language makes you do is like write a simple hello world program. And that's kind of like the moment where and that's a good exercise because it's some small computation which makes you used to a lot of the tooling, which is how do you compile this program, what does the basic syntax look like, how does the linter work, and things like that. So a similar equivalent in the ZK world, at least for me, is like this application called ZK Factors, where you try to prove to some person that you know factors of some number. And I know this doesn't sound like a very, very big example of what you could do with it, but it's a good start. And this could actually be very interesting in a lot of other scenarios where someone could delegate a bunch of, let's say, compute, and these inputs could be sensitive. So let's say there could be some escrow where you reveal the inputs when someone pays for your computation or things like that, right? So you can actually have some real like examples pop out of it. But let's discuss the proving flow. So, okay, I guess this is something that I should have relayed in advance, but anyway, this is being recorded, so it's fine if you cannot follow along. And I personally would say just watching it right now and then doing it later on is also perfectly fine. I can share this workshop with you. So you would need Circom installed on your system and Snark, and yeah, only Circom installed on your system if you want to do this workshop. If you do not have it installed, it's fine. You can just watch it. If you have it, you can try to follow along. Otherwise, feel free to watch it on your own. Uh, yeah, on your own luxury. So yeah, that's the flow of how you actually make a ZK application, right? And this has changed a little bit with ZK VMs coming in, but at least if you want to go through the traditional route of uh, writing through circuits, then that's how it will work. And if someone wants to talk about ZK VMs, I'm more than happy to talk after this call as well, that how the paradigm would look different if you do it with a ZK VM. But traditionally, you would just write your circuit in some high-level language like Circom, or in case of Aztec, it would be Noir, and you would compile this circuit. And our post compilation, so compilation of computation is something very uh, like common to anyone who has programmed. But what really changes in the ZK paradigm is that you generate two sort of keys. One is a a key for proof generation, and this key you call a Z key, and another key which is called as a verification key. And these two are derived from the compilation of a circuit. So every computation has a proving key and a verification key. And there's a prover, and the prover uses its inputs and its proving key to create zero knowledge proofs. And then the verifier takes the verification key, the proof from the prover, and uses it to verify proofs, right? So that's kind of like a general flow of how writing your first ZK circuit works. And the tech stack that we're choosing for now is Circom and Snark.js. So Circom will be the high-level language which we will use to write a circuit. And Snark.js is the tooling that we will use to generate these keys for compilation and everything else. Now, one thing that I have done here is that I have actually written my own abstractions on top of Snark.js to make it very easy for anyone to write their first circuits. So that's why I would advise anyone who's trying to follow along to just clone this repository. I'm putting it again here in the chat. Uh, yep. So now let me just go and try to, let's say, do And I will also try to explain on my behalf a few of the steps that we're taking here. So git clone zk101. Should happen pretty soon, I guess. Yeah, like this is slightly big in size, and now when I look at it, I'm wondering what makes it big in size. That's it's quite interesting. But yep, let's just wait a little bit more. Almost there. And if meanwhile I can explain that, okay, I guess it's done. So we have like, let's say open it in Visual Studio Code. Um, yep. So I guess, yeah. So when you will enter this particular uh, template, you will see that there's some boilerplate code, right? And the first thing you have to do is do an npm install. So there are some dependencies in this project, and you would have to install them before you can start doing few things. So just like how we usually have an src uh, folder, I have a circuit folder here which contains my main circuit. And you can imagine of template as being an abstraction over some computation, right? So templates are blueprints of circuits. Templates can be combined together, and templates have inputs and templates have outputs. So that's kind of like a basic 101. You can think of them as very similar to classes in object-oriented programming. And the first thing that you have to do is you have to define two signals. One would be your signal input for X, which would be the first factor, and then would be the signal output Y, signal input Y, and then you will define a signal output Z. So now the question is, what is a signal, right? And then, so signal is what you could say, it's very similar to electronic circuits. What really carries a value to some gate and from some gate. So in our case, like there are two input signals. We provide X and Y, and then we put it in a single, let's say, a multiplication gate, and then the value that it produces is Z, which is the output, and that's, let's say, the second, which is the output signal. And if you do not specify these inputs to be public, by default they are considered to be private. So you would have to create, like specify that they are public if you want to. And for outputs can never be private, and they are always public. So what we are trying to say here is to the user is that provide me an input signal X, Y, and like my output will be returned to the signal Z. And then what we will do is we will assign and at the same time constrain Z to be the product of X and Y. And what does that mean? So we are taking X and Y, multiplying them, feeding them to this output signal, at the same time creating a constraint. And what's a constraint? Constraint is, you could say, some relationship between, let's say, between values in your circuits that need to be hold true. So for example, if I want to say that X square should be some value Z plus Y, or yeah, something like that. So if I want to say, let's say X plus Y should be equal to Z, then that's a constraint. And I want this to be true for my circuit to be able to generate a proof, right? So that's what it means here. And then as we discussed, the first step is to compile it. And if you have done, and so what I've done is that I've created a lot of scripts which abstract away a lot of complexities that you deal with when you're working with Snark.js. So for now, I guess the first thing you would have to do is you would have to like give executable permission to all of these scripts. And then you can just go to scripts and then say compile circuit. And you can say that it has like one a constraint, and there are like two private inputs, one public outputs. It has been compiled, and all the compilation lives here, right? So there's a wasm file generated, which will be used for creating witnesses and a lot of other stuff. But we do have like a compilation here. R1CS is it stands for Rank 1 Constraint Systems. And if you're interested in understanding them, I'm happy to chat later on from this workshop. But I guess for someone who's new, this might be beyond the scope for them. And yep, so I guess we have compiled them. And then the second step is that if you remember, we have to generate keys. So that's like step 2, that we have to generate proving and verification keys. And that again, with the help of these abstractions are made, is quite simple. So you come and do say generate keys. And now what has started is this process of powers of tau. And meanwhile it's happening, let me explain what's happening. So powers of tau is a ceremony which is performed to create a shared like a secret value. And usually it is done in a multi-party computation setting. And there are few values which are called as toxic waste during this process, which should be removed, and no one should have them. Otherwise, people can, let's say, do certain attacks. So snarks have this dependency of this, uh, let's say, secret being generated safely. And people usually do multi-party computation, where as long as one party is honest, like the proof, like this generation of these secret values is considered to be sacred and can be relied upon. Right now, I just generated these values locally on my system, but in a real world system, you would do this with, let's say, multi-party computation. So now you can take a look and see that we have two keys, a Z key, which will be used for proving, and a verification key, which we will use for verification. Now, and by the way, like, so there are various snark protocols as well, and the one we are using is Plonk. So you can even use Groth, you can use Plonk, and there are, like, we are using Plonk for now. And I guess Plonk also has a lot of new updates right now. So then we will try, now to generate a proof, you would have to create this file called input.json, which provides the inputs for your computation. So I will say X is, let's say, 6 and Y is 2. So the project should be 12. And if I come and say scripts, generate proof, then you can see that I have two values. One is the proof itself, and you can see it contains like no details about any of the inputs. And then there's the public parameters required for verification. In our case, it is just the output, which is Z, and we can see that the public data is 12. So now I can try to prove to someone I know two numbers which when multiplied will result into 12. But they would never know whether I know whether this is 4 or 3 or whether it is 6 or 2. And if the number of possible factors is high, then like it becomes even more trickier to do so. And how do you verify this? Again, you can just leverage the scripts that are made and say verify proof. And it will say, okay, like Snark just says it's fine. Like I know two numbers which when multiplied results into 12. But what if I try to fake the proof? So I say, this is the proof, and the output that I know is for 12, or for product of two numbers, which will result into 10. If I try to do this, this will say invalid proof, right? So the proof is not valid. And as so long as, and this is interesting, right? Like it's a bunch of moon math, making it possible to prove that I know two numbers, which when multiplied will result into 12, but I'm not actually showing any of those factors. And I can at the same time prove the verifier, but at the same time not fool the verifier. So this indeed is like a really interesting construct that this moon math allows. And then like some final interesting things you can do with the scripts that are made is, and again, these are all made possible by Snark.js. These are just wrappers on top of it. But you can actually generate a Solidity smart contract. So you can say Oh, it says contract not found. Okay, good. So we can just say, oh, I see. So we would have to do a small fix to the scripts. I will fix them myself later on. But yep, and yep. So you can generate, let's say, a contract here. So I just do and say generate contract. And now there's a verifier Solidity smart contract specifically made for verifying proofs from this particular circuit. And I can then generate call data as well. So I can say generate call data, and then it will provide me EVM call data that I can uh, provide as part of my transaction to prove that I know output of two numbers, which when multiplied results into 12. So here you can see that this is the ZK proof. And the last one is the list of public parameters, which for right now is C, which stands for 12, and stands for C in hexadecimal notation. So that's like a first gentle introduction of how to write your own circuits, and yeah, like how to really work with them. And then I guess I have definitely bored you all a lot, but I guess like I definitely owe you a specific roadmap which could really be helpful, and I guess I should really upgrade this. But I would say definitely like what you should do next is spend a lot of time understanding Circom in depth, reading a few Circom libraries here and there, understanding how to use them, like learn a lot of Snark.js and how it works. And at the same time, I would say to look behind the scripts that I've written in my as part of my shell. So I've written a bunch of shell scripts which abstract away a lot of Snark.js stuff. So definitely read through them to get an understanding of what's happening in between them. And I would also recommend reading, let's say, the paper on Groth 16 and the paper on Plonks if you want to dive deeper into the maths of it. And there's this book called The Moon Math Manual, which I would really recommend for some of you to read, as it helps you dive deeper into these primitives that make all of this moon math possible. Uh, and before I leave, like few real world use cases of Snarks, like scalability. What I mean by that is that you can have a bunch of. So again, this workshop was created back when ZK EVMs were the AGI kind of a problem of crypto. And what you can do with, let's say, ZK proofs is you can prove any arbitrary computation, which means that rather than doing computation on Ethereum, you can just do that computation anywhere else and just create a ZK proof that whatever you did indeed is correct, right? So ZK is the end game for scaling. And I think that's where like all this scaling will happen. You will see layer 2s and co-processors and a lot of other things coming up, which do computations outside of blockchains, at the same time provide verifiability of the compute itself. So you will also see, and I would even say ZK oracles would be a big use case where like you could just prove that and again, this would be co-processor, but you could just say on some specific financial feed, you could do some sort of computation and then prove that this is what the result would be. For example, the average price of something that's happening on chain, etc., and a lot of other things. And then the second one would be privacy. Ideas like Polygon ID, which I guess has now spawned out, and it's called Privado ID, where you can like build a whole identity system from scratch with privacy built into it. So for example, I can prove that I am above the age of 18 without revealing anything about where I live and XYZ. And it's an interesting protocol. I would definitely suggest looking more into Polygon ID, or which is Privado ID right now. I had the honor to work there for some time and contribute to the protocol. And I think it's one of the best use cases of ZK proofs out there. So yeah, thanks. Feel free to give me some feedback, whatever you think about this workshop. And I'm more than happy to answer any question if someone has any. So yeah. And I hope I didn't bore you all a lot. Yeah.
No, it was very interesting session we could get our hands on. And yesterday also we had a little introduction to Circom, long and stuff. And it was a good revising concept and an hands-on as well. It was great having you here. And time for questions. If you have any questions, please do drop it in the chat, or you can also, I think you'll have uh, microphone enabled, so you can unmute and ask your questions.
I see. It will be good to talk about few simpler use cases that new dev should be looking at working. I guess so. Like Seth, are we talking? Oh, I see. So I guess we are talking here for from the perspective of learning and getting better at this stuff, right? Like not with them being, let's say, some big real world projects. Ah, I see. Good. I got it. So yeah, so I would say like few really interesting things that you could, let's say, slightly like keep building upon from here on. Could be, let's say, a Sudoku, like a ZK based Sudoku game, and you can actually launch it on a web browser and put it on chain, where people are playing Sudoku. There's a Sudoku puzzle published on chain, and then two people are trying to solve it, and they just give a ZK proof that they indeed have solved it, right? Uh, then I would say some other one could be voting. So that was my first big ZK project, where I wrote circuits to allow for proving of someone voting for something without revealing their EVM address, and allowing for verification of that on chain. So I would definitely say that could be really interesting use case. You could even try to build a small roll up, like something which is very simple, like just payments. That's it, and then you try to prove it through it. And I would say that another piece of information is that there's this group called zkBankai, which is giving right now grants for building things with Circom. So I guess you can also look into their website and see what ideas they have suggested, and probably apply for a grant as well if that suits you well. So I would say, yeah, like if I was there and if I just have to build POCs to have fun at the same time, learn better, I would be building basic games or things like private voting, which can be done like in a 2 to 3 day time span, and probably also putting them somewhere on chain with the front end so that people can play around. Nice. Can I give a please small intro to ZKVMs? Okay, I guess I will answer firstly Bosco's question and then to Emmanuel's. So to answer your question, a zkVM. Okay, so like the industry started with writing circuits, and the time of development of ZK projects became extremely high, because you have to write these custom circuits every time your demand changes. You have to like write this almost assembly like looking code, and it becomes, and only very few people can write it. And yeah, it's like very hard to find talent, it's very slow to develop. So that's where like few people started working on zkVMs. Notably Starkware is a good example out there. I guess Maiden is working on it. I guess Aztec has that with Noir as a language, and a lot of other people. And RIS0 has it, SP1 has it. And then the idea is that you create circuits that proves the execution of some VM architecture. So for example, you take RISC-V architecture, which is a very popular architecture, and then you create circuits for the RISC-V architecture, which means anything that is now written inside RISC-V can be ZK proven. So you write circuits once, and those circuits allow you to prove any computation that's done in the RISC-V based system. So which means that you can just take any Rust C++ computation, which is compiled for the RISC-V architecture, and then just run them, and run them as normal computation, and it will eventually be proven. Now, this does come with a trade-off, which is that you are emulating a VM, like a VM inside ZK circuits. Uh, so, like, this comes with the overhead, right? So, sometimes, now again, this is a big debate whether ZK circuits are better or VMs, but sometimes like ZK VMs could like really perform poorly compared to ZK circuits written from scratch. Although this argument has to be justified with a lot of facts, so we have to see. But right now, like ZK VMs, main focus is allowing people to write programs in normal looking programming languages, Rust like programming languages, C++ like programming languages, and them not even caring that how does all of this machinery work, and being able to prove their computation. So yep, that's kind of like a zkVM introduction. I hope that answers your question, Bosco. And feel free to, let's say, ask again if something wasn't clear. Uh, Coming to Emmanuel, okay, so could you describe, for example, in the Groth 16 proof system, at what point each of the properties that make a ZK snark truly satisfy hold, that is where and when completeness and soundness and zero knowledge hold, because the simulator extract is necessary to ensure soundness. I didn't completely get the question. So saying that where and when soundness, completeness, and zero knowledge hold. Could you like elaborate it? Like, are you asking specifically in the protocol, like, or what primitives do we use in the protocol to make sure that all of these things are holding true? Or yeah, like I couldn't completely get the question. So you're asking in the, are you asking in the paper, or let's say in the construct of, let's say, a Plonk, or so let's say for example in the Plonk, I can tell you, uh, let's say where so the primitive which helps you get these properties of completeness, or let's say soundness, or zero knowledgeness, is a polynomial commitment scheme. So you have these you have this zk snark is needed for these, yeah, they are needed for these three properties, but like I guess I can explain what primitives helps you achieve them inside a snark protocol. So from my understanding, it is polynomial commitment schemes which eventually allows you to get this. So I guess in case of Plonk, we use KZG. And what a polynomial commitment scheme is that it allows you to prove, it allows you to firstly commit to a polynomial that you, let's say you are working on this specific polynomial, and then be able to prove the evaluation of this polynomial at different points, right? So what happens, let's say in the case of Plonks, is that, but even in the case of, let's say, Groth 16, is that you take some computation, you create it into some intermediate representation. In case of Groth 16, that is R1CS. In case of Plonks, this is like polynomials, like, and then you take these polynomials, you do something called as a Lagrange interpolation, which allows you to get a specific single polynomial, which uh, which denotes all of these polynomials combined. So like this is a polynomial which like kind of encompasses all of these polynomials combined. And then you commit to this polynomial through these polynomial commitment schemes, which indeed allows you to like prove the fact that you can open this polynomial at various points in zero knowledge. So, and then there are like a lot of other assumptions as well. uh, I guess, let's say, for example, in the trusted ceremony, that this toxic waste is uh, removed, and other things like that to, uh, let's say, remove any kind of adversary here and there. So, for example, ZKEMs are not really ZK. They do not comply with zero knowledge property. They also, oh yeah, so I guess now I get what you're trying to say, that, uh, yeah, so like any, if you look at a ZK VM, right? Like in a way, if you actually want, you can make it private, right? It's not a technical matter. You could actually look at any circuit. If, let's say, for example, in my multiplication circuit, I make all the signals public, right? Now there is no zero knowledge left. Like I'm just like revealing all of my inputs and my outputs. The only thing that can be skipped is the verification of the circuit. So yeah, you are true here that right now in crypto, most of the cases don't actually use the zero knowledge part, where I can prove that I know certain inputs to the specific computation, which would result into the specific outputs. But you could say that like a computation, like in like a ZK VM, where like there is no ZK, like we're not trying to prove anything through zero knowledge. The underlying technology is still same, right? The Groth 16 is still same. The only difference is that all the uh, inputs and the outputs are public. Outputs are always public, but all the inputs are public, right? And that's why there are no more ZK. So, like, but a true ZK based system would be a system where, let's say, I could hide certain inputs or all of the inputs. Like in an ideal scenario, you would hide all the inputs, right? But I don't think you can build the real business logics on top of it. So yeah, I would say like they are like still ZK circuits. Like Uh, and like there's a difference between a snark and a zk snark, right? Like you could say, like you could prove that you know some knowledge uh, without it being zk, which means that without hiding those inputs. So if in a succinct way, let's say if I do a computation in an hour, right, and I can, let's say, prove uh, that I know, like I've done this computation correctly, right? Then if I do not hide any of my inputs, you could say that that's not, you can just call it a snark, like it's a succinct uh, piece of cryptographic object, which is proving that I know some, like some piece of knowledge. And it becomes a ZK snark when you can hide inputs. So that's to answer it a little bit. And any circuit that, any like system which uses protocols like groth 16, but all the inputs are public, it's the still same ZK based scheme, but they're just making all the systems public. But yeah, there is a difference between a snark and a ZK snark. So yeah, you correct it. Yep, thanks. Any other question?
I think we don't have any more questions, but it was great interacting session. Thank you for answering all our questions, and thank you for having here. It was a great session, and I hope a lot of other participants will also watch the recording and will get benefited by it. Yeah.
Yep.
Yeah, please.
Yeah, thanks. Thanks for inviting me. Oh yeah, go ahead in manual. By the way, like if you have questions, you can also send me to me later on async on Telegram. So I guess that works for me as well. But
You
yeah,
can also
feel
just
free
turn
to.
on the microphone so you can also speak if you prefer.
Yep. Can I talk a little bit about Plonky 3? Yeah, why not? Uh, okay, yeah, sorry. So I guess Plonky 3 is this set of cryptographic primitives which have been made by Polygon. And the goal of Plonky 3 is to if you have looked at ArcWorks, right? What ArcWorks does is that it provides you a lot of primitive implementation. So like polynomials, and then groups and finite fields, and a lot of these implementations, which you can then combine to build any cryptographic protocol you want on top of it. Plonky 3 is a similar attempt. The idea here is that you build a lot of primitives which are required for building stacks and like proving systems, and then you make them as a modular library that people can then use to build anything that they want on top of it. So if you look at Succinct and the SP1 RISC-V based VM they have made, it uses Plonky 3 under the hood, where they have used these components, these modular cryptographic components, and combined them to make a proving system for the RISC-V VM, right? Plonky 3, as far as I know, is stack based, and all the components it provides is for proving stacks. And I guess now they are also working on extending it to provide support for circle stacks, which should be like a new thing that would be adding to it soon. But yeah, like in short, it's a modular uh, it's a library of cryptographic systems, cryptographic elements, which you can then combine to build any proving system that you want on top of it. Does that answer your question? Like, thank you. Cool. Yeah. Thank you, everyone. Thanks for having me. And
Thank you
yeah,
so much,
feel
sir.
free to.
Thanks everyone for
Yep.
joining.
Yeah, Bosco, you had a question. Feel free to. Oh, no worries. Yeah.
Okay, got it. No worries.
All right,
Cool.
thanks, Harsh.
Thanks.
Really appreciate your time.
Yep. Thanks, F, for inviting me, and thanks everyone here for joining. And feel free to reach out if you need any help, or if you have any doubts. More than happy to answer on Telegram. I guess this is my Telegram in case someone needs to reach out. I might be slow, but will try to answer to the best of my capacity. Yep. Thank you.
Really appreciate it. Thanks.